Okay, class. Now coming to the of current electricity. So electrostats we completed in the last class. Who all have joined? Zain, Hanifa, Hamza. Okay. So basic thing that you have in electric current is the definition of it, rate of flow of charges. Now from this part, from this initial part, you get questions on the rate of change of charge means how much charge is changing with respect to time. Now, what type of questions come? Two type of questions come from this directly. Either somehow you'll have to calculate the value of charge and divide it by time to get the value of the current, or you have to differentiate it. Now, when do we differentiate? When do we take the average value? We differentiate it when we have to find out the instantaneous current at a very particular time instance. And average if we have to find the change for a duration. So see the question, read it properly, whether it's duration given or any time instant is given to you. Fine. So this is the difference between the average current and instantaneous current, and rest of the things from current are direct. Otherwise now, apart from this, you will be getting questions which will be involving to find out the value of current by this method and put that value of current in some other form. Like, let's say in magnetics, you have formula of solenoid as B is equal to mu naught Ni. So maybe you will not be getting direct value of current. So you will be getting value of charge and time. So that with the help of the value that are given, you have to first calculate the value of current and then put it in the whatever formula you have for solenoid. Clear? So like this questions come. Otherwise, this part is quite direct. Now, drift velocity, very, very important topic. So what is drift velocity? Every electron will be moving with a certain velocity. Every electron will be colliding with itself also, with the wall of the conductor also, with the positive ions also. So it means every electron will be having different values of velocity. The average velocity with which the entire conductors are moving, you can say simply all the electrons are moving. Fine. Velocity with which electrons drift towards the positive end of conductor under application of electric field. Just a second, give me a second. So all the electrons will be moving. We calculate the average velocity of all the electrons so that we get a net value. Like if I say the electrons are moving with velocity 5 meters per second within this conductor, within this wire. So now it does not mean that every electron will be having 5 meters per second. It can happen one electron is having 4.9 meters per second, one is having 4.8, one is having 5, one is having 5.1, one is having 5.0. When I have calculated the average, I found that the average of all the electrons is coming to be 5 meters per second. So this is what is meant by drift velocity. Velocity with which all the electrons drift towards the positive end, velocity with which all the electrons are attracted towards the positive end of conductor under the application of electric field. Fine, this is average thermal velocity. Now, relaxation time means when the electrons collide among themselves, they collide and then it is a very, very small time interval, very short time interval before they begin the next collision. Like one electron has collided with itself, it will rest for a very short duration and then it will begin the collision with the next of the entity that is present. So that is known as relaxation time. Again, we'll not be considering just the relaxation time of one electron. We'll be having entire velocity. We'll be considering all the values of relaxation time for every electron. So this is known as relaxation time. Clear? Now this derivation class is very important. There are a lot of chances you can get a full 5-marker derivation from drift velocity. So drift velocity is minus small e capital E tau by m. Fine. Then you have from here, this relation is also very important. More than drift velocity's formula, relation between current and drift velocity. This is very, very important class. This has a lot of chances in coming in the exam. So please see the derivation once and through the notes, because if I discuss every point of derivation, then your syllabus will not be completed. So I is equal to NEAVD, where N is number density of electrons, E is the electronic charge, that is 1.6 into 10 to the power minus 19. A is the area of conductor, and drift velocity is the velocity, drift velocity. VD is drift velocity. So I is equal to NEAVD. Now, if you look at this formula, it seems that current is directly proportional to area. Right, if you look here, this current is directly proportional to area of cross section, but it is independent. This through the formula, it seems as if current is directly proportional to area, but practically through the applications, it is noticed that current is independent of area of cross section. Reason is that current is amount of charge, rate of flow of charge. So whatever amount of charge has entered, right, whatever amount of charges have entered, that will only exist, whatever be the area of cross section. Even if the area expands, the amount of charge that has entered, it will only exist. That's why this is independent of area of cross section. But drift velocity is inversely proportional to area from the formula. That is valid. If area is more, velocity will be less. If area is less, velocity will be high, inversely proportional. Then you have Ohm's law. A direct question comes, 3 marker questions comes on Ohm's law, where you have to mention the law, you have to mention the formula, and it's better if you plot the graph as well. Now see, it says that at constant temperature and pressure, potential difference applied across the ends of conductor is directly proportional to current. Fine, and here you get a constant, which is resistance. The value of this constant is the resistance. So resistance we'll see just now, I'll also tell you. So this is the basics of Ohm's law. Let us practice one question from here. Okay. Hanifa, some error is there in the calculation. Let me discuss then see wherever you committed an error. If the resistance of the wire is RO, what will be its new resistance if it is stretched? N times the original length. Now see, if you are increasing the length, one quantity that will remain same is volume. Volume of the wire will not change. No? You are increasing the length, but you are not adding some amount of the material so that the volume should increase or decrease. So that's why the volume will remain the same. So original volume and the final volume and the new volume, both will remain the same. V and V dash will be the same. And volume of a cylinder can be written as area into length, area of cross section into length, and new area of cross section into new length. Right. And what will be its new resistance if it is stretched n times? Means new length is n times the original length. So AL will be A dash NL. A dash is A by N. Now see, one more formula we'll see that is used here. Resistance, one more formula is rho L by A. So if you write R is equal to rho, resistivity, length by area divided by R prime. So that will be rho, nu L is N times, no L, N times L. And area is A by N. So everything will get cancelled. A, L, L, rho, rho. R by R prime will be 1 by N square. R prime will be N square R. Now class, this is not just a question. In many questions, sometimes you will be given just this part only. N times it is stretched. So directly write down the formula and use it as a formula also if it is required. Note it down, then we'll discuss the rest of the portions. Now resistance, as we have discussed one formula, this another formula will not come in your numericals, this formula, but the derivation will be asked. This ml divided by ne square a tau. So do this derivation thoroughly. You all have the links of the notes, so open it in your browsers and revise it. Fine, so this is resistance, and resistance depends upon length. It is inversely proportional to area of cross section. It depends on nature of material, and it depends on temperature. Now for temperature, you have a full section that we'll discuss later on. This formula, we have done the question. Resistance is rho L by A. Now what is this rho? Rho is sensitivity, resistivity. Resistivity of a material is defined as resistance of a unit length of unit area of cross sections. Means in this formula, rho is equal to RA by L. You put A as 1 meter square, L as 1 meter. You will get rho equal to resistance. Fine. So resistivity will be exactly what is the formula for resistance without length and area, because those will get cancelled. Right. So it will be M by Ne square tau. For resistance, you have ML by A Ne square tau. For resistivity, you have M by Ne square tau. And it is also independent of length and area of cross section. Now, how questions you will get? You will get the questions as just now we have discussed that type of question only. But no, some additional questions will be having. In addition to that, it will be asking what will be the change on resistivity if it is stretched to by n times or increased by 10% like this. So resistivity is independent of length and area of cross section. So directly write it, resistivity will not change as it is independent of length and area. It just depends on the nature of material. You change the material, resistivity change. It's like density. Density you have for water, it is 1000 kg per meter cube. So even if you take a glass of water, the density of one molecule will be 1000 kg per meter cube. And if you take the water from one drop from the ocean, that will also be having the same density, that is 1000 kg per meter cube. So density won't change because it is material dependent property. But if you change the material, like instead of water, you're taking the density of copper, you're taking the density of brass, you're taking the density of zinc, every material will be having its own density. Similarly, it's the case of resistivity. Resistivity has its own formulas, its own values for every material. It depends on material, but it is independent of length and area of the cross section. Now you have these two terms, conductance and conductivity. See, just remember the term resistance. Whatever is the formula for resistance, reciprocal of resistance, inverse of resistance is conductance. So SI unit for resistance is ohm. So SI unit for conductance will become ohm inverse. And conductivity, inverse of resistivity. So sigma is equal to 1 by rho. That is, conductance is denoted by capital G, and conductivity, sigma is denoted by, conductivity is denoted by sigma. Then you have current density. Current density is current per unit area. This will also not separately be asked to you. Usually it is asked in the form of question only, where using one of the formulas, you have to find out the value of current density, and then using that, you put it in the other formula that is given. And class, this can be asked separately, macroscopic form of Ohm's law. So microscopic form of Ohm's law is just this statement, J is equal to sigma E. J is the current density, current per unit area. Sigma is conductivity, the inverse of resistivity, and E is the electric field. Now mobility is drift velocity per unit electric field. Whatever is the drift velocity's value, if you divide it by the electric field, you get mobility. So some of these terms are sometimes asked in the exam, and many of the times they are used in the formula. Then we have the variation of resistance with temperature. One formula is also there, but just see first graphically. See, when you increase the temperature, if it's a conductor, for conductors, like let's say we have taken metals, copper we have taken. So if you will increase the temperature, value of resistance will also increase, and the value of resistivity will also increase. Both will increase, right? But you will notice that till this point, 0 degree, you're getting a non-linear variation. Means current is, resistance is slowly increasing, but this is independent of temperature. It's not necessary if the temperature is increasing, the density or the resistivity or resistance will increase for surely. No, It can increase also, it can decrease also, it is non-linear. But after it crosses 0 degree or 273 Kelvin, it will increase along with the increment in the temperature. That is, it will have a linear variation, straight line graph. So this completes your conductor's graph. Non-linear part plus linear part. If you do not draw the linear part, that will make your answer incomplete. Alloy has the same case, that resistance and resistivity will be increased by increase in temperature. But difference between alloys and conductors is that conductors have their variation quite significant. But in the resistance and resistivity, the variation is very small. Very small variation is observed. Then you have semiconductors. Semiconductors, we did a complete lesson also. So most of the questions from semiconductors will be from that chapter only. PN junction and all that we discussed. Now, for semiconductors and insulators, you get a hyperbola. Why? Because this is inversely proportional. If you increase the temperature, resistance or resistivity will decrease. And if you decrease the temperature, resistance and resistivity will increase. Then superconductors is not important. This formula is important. RT is equal to R naught 1 plus alpha T minus T naught. This formula is important. Let's practice a question also on this. See, it says that resistance of a conductor at 20 degrees Celsius is 3.15 ohm and at 100 degrees Celsius it is 3.75 ohm. So you have to determine the temperature coefficient of resistance. See, the formula is RT is equal to R naught 1 plus alpha T minus T naught. RT is the resistance at room temperature. R naught is RT is the resistance at any temperature. R naught is resistance at room temperature. Alpha is temperature coefficient of resistance. T is the time period that is given, and T naught is the time for room temperature. Temperature for room temperature, and capital T is the temperature given. So here, if you look, two formula will be constructed. Because two resistance are given and two values of time are given. So R1 will be equal to 1 plus alpha T1, and R2 will be equal to R naught will also be there. R naught 1 plus alpha T2. When you divide it, R1 by R2, R naught 1 plus alpha T1, R naught 1 plus alpha T2. R naught gets cancelled. Now from here you can write R1 into 1 plus alpha T2 is equal to R2 1 plus alpha T1. Now cross multiply, or best is you write the value of alpha. Alpha will be R2 minus R1 divided by R1 T2 minus R2 T1. Fine. Now alpha's value, if you put see here, T1 is 20 degrees Celsius and R1 is 3.15. This is 3.15. So this is 3.15 ohms, and T2 is 100 degrees Celsius and R2's value is 3.75. So everything is given, just substitute in this format. Okay, noted down. The next topic is terminal potential difference, internal resistance, and EMF of a cell. These three topics together. So internal resistance means resistance that is offered by the electrodes and the electrolytic solution of the cell. See, when you see the structure of a cell, inside the cell, you will find two electrodes are also there, cathodes and anodes, which we commonly call it. And there will be a solution which is known as electrolytic solution. So positive and negative electrodes will be there in electrolytic solution. So that resistance that this electrolytic solution will be offering to the nodes, by the electrodes, that is known as internal resistance. So electrodes, both the electrodes, your cathode anode plus your electrolytic solution. This adds up and this gives your internal resistance, which is usually denoted by small r, and many a times it is omitted in the circuits of the cells. Now see, EMF means maximum potential difference across the terminals of a cell in an open circuit. This is basically the potential that is present across the external resistor, capital R. That is present across the external resistor, capital R. And this is difference of potential. But there is another term which we call terminal potential difference. Now, what does this mean? Your EMF was valid for closed circuit. Terminal potential difference arises in your terminal potential difference arises in closed circuit. EMF arises for open circuit. And potential difference across external. Okay, I just mentioned external there. No, see, closed circuit and external resistor will be for terminal potential difference. Internal resistor and open circuit will be for EMF. So EMF and terminal potential difference are two distinct quantities. Potential properties will remain same in both of these. Then some formula are there. See, total resistance will be what? Whatever is the internal resistance of the circuit plus whatever is the total external resistance of the circuit, that will combine and it will give you total resistance of the circuit. Potential is EMF of the cell. So current is EMF divided by the total resistance R plus R. In this individually external resistor, if you want to find out the potential difference across the external resistor, it will be the current in the circuit multiplied by the external resistance. And if you have to find out for it for the same internal resistance, you will have to multiply the current by the internal resistor's value. So this is one formula, E by R plus R, and these two, V is equal to IR and E divided by R plus R, this formula also. R plus R multiplied by R. So the value of current just multiplied with the external circuit. And another you have it as the terminal potential difference, which is EMF subtracted from the potential difference across internal resistance. So V is equal to E minus IR. So let's practice numericals from this. Yes, class answers. Nobody has answered. See, EMF is given to you. EMF, a battery of EMF E, internal resistance R is there. Current is given 0.5 with an external resistor 12. Then current is given 0.25 with external resistor 25. So in the equation, E by R plus small r is equal to current. This value and this value is given for two equations and these two are unknown. So EMF will be, for the first part, it will be current 0.5 amperes multiplied by the total resistance 12 plus small r. Then the EMF will be 0.25, 25 plus r. So what you can do, we can substitute it or we can equate both these equations. So that's better. 0.5 is equal to 12 plus r. 0.5. Equate both these equations. So from here 50 and 2. So 24 plus 2r is equal to 25 plus r. So r will be 1 ohm. Put it in any formula. E is equal to 0.5 multiplied by 12 plus 1, that is 13, that will make it 6.5 volt. So R will be 1 ohm, EMF will be 6.5. Note it down quickly, class. Class series parallel combination are very easy. For series combination of resistors, you reciprocally, for a series combination of resistor, you just algebraically add all the resistances together. And for parallel combination, you take the reciprocal addition. So that is series and parallel combination. Let us just complete rest other topics as well. Then we can, whatever time will be left, we'll be practicing numericals. Then Kirchhoff's law statement can also come to Kirchhoff's first law and Kirchhoff's second law. So Kirchhoff's first law is also known as junction law. So this means whatever current is entering a junction. Junction means any crossings of two wires, intersecting two wires. So when the currents will come at a junction, all the currents of the current will leave the junction as well. So whatever current comes is actually equal to the amount of current that leaves the junction. So whatever current is pointing towards the junction, by sign convention, we call it as positive, and whatever are leaving, we call it as negative. So net sum of the current is zero at any junction. So this is Kirchhoff's first law, which is junction law. It says that the algebraic sum of currents at any junction is zero. Then second law, this is also known as Kirchhoff's current law. Then you have KVL, which is Kirchhoff's voltage law. Kirchhoff's second law is also known as loop law. So here net potential is zero. Mainly we use this also. We use both the laws to solve our answer. So potential is zero. Now around any closed loop of a network, algebraic sum of change the charges in potential is zero. Whatever will be the sum of changes in potential, that will be equal to zero. Net potential, you will equate it finally to zero. Now how to solve the questions of based on Kirchhoff's law? See, for cells, potential, if you are moving from the direction negative to positive terminal, then you will write voltage as positive. And if you are moving from positive to negative, you will put it as minus E, negative, minus E. So plus E and minus E. Then V is equal to IR is the formula using Ohm's law. So what we'll do, one current will be flowing from the positive to the negative terminal of the resistor, from higher to lower. But if you are also moving along the direction of current, in the direction that you take, no, anti-clockwise and clockwise. If you are also moving in the same direction, you put it as positive. If you are moving in the opposite direction, take it as negative. This is all about Kirchhoff's law. You just have to apply all these things in a single formula. Then from potentiometer is not coming in your case, no need to do that. Series, yes, this is more important. Combination of identical cells, series and parallel. So if identical cells are connected, let's say n number of cells are connected which are identical. So current becomes N into small e, N into capital E, which is EMF, N into E divided by R plus N into R. N is small, R is small. So NE by R plus NR. R is internal resistance, capital R is external resistance. Now, two cases you will get when capital R is very much greater than small r, and second case when small r is very much greater than capital R. Now, small nr plus capital R, this is almost equal to the resistance. Small nr means nr in plus capital R, this is almost equal to the resistance. So, current will be NE by R maximum. So, you will prefer series combination. Now, see if small r is greater than capital R. Here, small n into small r will be of much greater significance than an external resistor. So you will write I is equal to NE by NR, NN will get cancelled. So I will be equal to E divided by R. So two cases we have seen, external resistor very much greater than internal resistor, and internal resistor very much greater than external resistor. This is for series combination. So in which case you're getting the maximum current, you're getting it for the external resistor greater than internal resistor, the first case. So if you are given external resistor's value larger than internal resistor, you go with this case, prefer this case first. Fine, then you have parallel combination. In parallel combination, equivalent EMF will remain E. Why it will remain E? Because it is in parallel combination. So current divides, but voltage does not get divided. So here, if m number of cells are present, then your formula becomes I is equal to ME divided by MR plus R. M into capital R plus R. So two cases are there. External resistor greater than internal resistor and internal resistor greater than external resistor. So MR plus R is almost equal to MR. In that case, you get I as E by R. And when your small r is very much greater than capital R, you get MR plus R almost equal to R. So here, see, here you're getting more amount of current in the second part because M is also getting multiplied. In the first part, you had E by R, but now in the second part, you are having M times E by R. So it is getting increased by M times. So you prefer parallel combination if internal resistance is greater than external resistance. If value of external resistor is greater than internal resistor, then you will directly put in the formula. Then you will prefer series combination. But if internal is greater than an external resistor, prefer parallel combination. Because we have, I think, discussed in the class also, some questions are there based on this. Lastly, you have mixed grouping. In mixed grouping, the formula becomes Mn into E divided by Nr plus Mr. And if you have to get the maximum current class, this is used a lot. N into small r is almost equal to M into capital R. Fine. N into R is almost equal to M into capital R. Now let us practice some questions. See, resistance value R1 is inversely proportional to conductance. So R1 will be 1 by G1. R2 will be 1 by G2. And R3 will be 1 by G3. Now see, for series combination, R will be equal to R1 plus R2 plus R3. So here 1 by G will be equal to 1 by G1 plus 1 by G2 plus 1 by G3. So if you take the LCM you will get it as G1 into G2 into G3. So that will make it G1 into G2 plus G2 into G3 plus G1 into G3. So this is 1 by G. When you have to write down the value of G, this will be reciprocal G1, G2, G3. G1, G2 plus G2, G3 plus G1, G3. All right, note it down. one more question is, I have written it. Let me just discuss it with you all. See this question, it says that 12 cells each of EMF 1.5 volt and internal resistance 0.5. These are arranged in M rows, each containing N cells connected in series. You have to find out the value of Nm from which combination would have maximum current through external resistor of 15 ohms. See, when maximum current is mentioned, directly write it as N into small r is equal to M into capital R. So from here, and if you put it values, you will get N square as 36, N will be 6, and once you get the value of N, you can get the value of M by putting it in the same equation. Note down this question as well and text me done once you have completed this. All those who have completed this part, you all can leave. Next, we'll start with the magnetics revision in the next class only. All right, thank you so much.